way. Okay. So I will put the recording of the lecture so you can refer to them, and as well as the full, let's say, slides of the course, so you can browse them and look at the resources. And yeah, as well, everything is streamed on YouTube. So there is a YouTube link on which you can catch the stream of the course if you cannot come to class. You can comment on the YouTube thing. I'll try to look at it if there are any questions for people following from YouTube. And as well, I will try out this thing, which is called Slido. So if you have a computer or a phone handy, you can go on slido.com and enter this code here. And this, basically what it allows you to do is to send comments or questions live. Everybody can see the comments, they are anonymous. And so I would prefer for people who are in class to just raise your hand and ask a question. But of course, sometimes it's not that easy to do. So you can, of course, send a question textually to this thing. And through this, I will also do some quizzes or polls to see how people are following. So if you can try, I mean, if you have a phone handy or a computer, try to connect to this thing. And we'll test the first poll to see if it works. Yeah. So if there are not enough chairs, you can get some in the hall. So I will launch the first poll. Yeah, okay. So here I can show you the live results in principle. Yeah. Okay, so we'll use this for questions and also sending comments or whatever. Okay, so it seems that most people come from physics as I expected. It's a pretty good, yeah, okay. So the results of the poll are pretty good representations of what fields are in artificial life, actually. So it's a very good mix of life sciences, physics, and computer science, and also a bit of math, as we can see, a bit of math. And yeah, okay, perfect. So just a bit about me. So I'm actually a physicist by training. So my PhD was in theoretical physics. And I've been working on A life for now about a year, although I was interested into it from a longer time. And so, yeah, so the goal of this full course will be to really give a broad overview of what is this field of artificial life, because it's a very small field. Okay, not many people are working on it if you compare it to something like theoretical physics or something like that, and it's not as well known. Okay, so most people, when you ask them, what is artificial life, they are not able to answer. Okay, or they have even never heard of the term. And so, yeah, the goal of this course is to give you both. It will be separated. We'll see afterwards the plan for the course, but there will be some parts which will be theoretical. So some theoretical results that can show, okay, how can reproduction arise or stuff like that. And then there will be also a big part which will be more like practical. So looking at some artificial life models, how did people come up with, how to implement them, and what do they show. Okay, so I'll stop the first poll and I'll start the second one, which is exactly about artificial life. So I'm quite interested to see if people knew about it before the email. Very good. Nobody's claiming my seat. That's nice. Okay, so actually 70% of people have actually heard the term before. That's more than what I expected. Okay, very good. And so, okay, is there any other technical stuff I want to say? So for the people who arrived a bit late, you can join to answer the polls, etc., with this on slido.com and with this code. I will try to. Whoops. No, that was not what I was supposed to do. Okay, I will go back to the code, but this is it. But most people seem to be on it because we had 30 answers, so that's good. And let me just open the question and answers. Okay, So the goal for today, it will be quite relaxed. Today will be no technical stuff, not at all. The goal is just to kind of get a broad idea of what is artificial life, the field. And I will also try to give a brief history of the field. So this will be not at all complete or exhaustive, but I will try to go through the more important, let's say, checkpoints for artificial life during the years. And that way you can get a sense of what we will study during the semester. Okay, and of course, if you have any question, you can stop me at any time. You can either raise your hand or just ask the question. I will stop, or of course, send the question on this Slido. But okay, so before that, are there any questions about the course, some technical stuff or anything? Yes? Yeah, so these slides, I will put them, I haven't yet, but I will put everything on the website. So we'll be able to access them. It will be basically a web page where you can access everything. So I hope people can hear on YouTube, but I think I tested. So if you cannot, you should protest. Okay. Great. Oh yeah, one last thing, just for the evaluation part of the course for people who have actually signed up on ES Academia. The idea is that it will be very relaxed. It will be either pass or fail. Okay, I expect pass will be very easy. And the idea is just that you select a very small project that should take you like 8 to 12 hours. That's the claim thing that you should spend on it, on any topic of the course. So if you're in math, if you want to do some proof about something we covered or something like that. If you're in physics, you want to do some experiment, even a real life experiment, or some simulation. If you want to code a little model that you had in mind or recode something we saw in course, anything goes, okay? Just pick a small project. If you're unsure if it qualifies, you just ask me, it probably qualifies. And at the end of the day, we'll see if we do like a very brief oral presentation or a very small report of like 3 or 4 pages or whichever you want. And then, okay, if you spend a reasonable amount of effort on it, you will pass. I think we are allowed to say pass or fail in these doctoral courses instead of giving a grade, but yeah. So it will be very relaxed, don't worry about this. Okay, so let's start actually into the meat of the project. Oh yeah, last thing. So I'm trying this thing, we'll see if people like it or not. I have essentially this notebook, which will act as slides so that I can live add some information if something is missing. So there will be quite a bit of text on screen. And this is on purpose. So this way, if you get only the slides, you're supposed to be able to understand more or less everything. And if I need to add something, I will. And so this will act as my slides, and we'll see if it's too much text or whatever. I will ask you after a few weeks, and potentially we'll change things. But for now, we'll go with this. All right. Okay, so artificial life. So let's start by trying to defining this term artificial life. What does it mean? So one way to speak about it is to say that artificial life is the field which tries to understand life as it could be. Okay, and when we mean as it could be, we mean as opposed to life as it is on Earth, okay? Because so far we just have one example of life, and it's life on Earth, okay? We don't have other examples. And so the goal of artificial life is to try and distill what does it mean to be alive, or what is life, in more abstract terms, okay? Life as it could be. So we say, okay, we define life as this and this and this. In particular, life on Earth satisfies these conditions. Of course, this is a requirement. But it can also be satisfied by some other system which lives, for example, inside a computer or inside another planet, or even on a network of things, like, I don't know, on the network of Bitcoin or something like that. So the goal of artificial life is really define life as an abstract concept, life as it could be. So what is life more generally than life on Earth? This is the broad goal, okay? And then you can cut this up into several big questions. And this is from a review of the big questions of artificial life, which I've linked here. And so I did a condensation of those, the ones that I'm more interested in. And so the first big question is, how does life arise from the non-living? Okay, so we know that this has happened on Earth. Okay, we had first just planets, some rocks, some minerals, everything inert in some way, and at some point just life appeared. Okay, at least that's what we think. And so the question is, how does this happen? When does this happen? Is it common? And so to answer the question, you need first to define what is life. Okay, this is already a very complicated question. Nobody agrees on this. But it's clear that if you want to define life, you need first to define what is, let's say, a creature or an entity, right? When you look at a soup of particles, and then there are some particles clumping together, moving around, how do you define that, okay, this clump of particle is one thing, and then this thing can reproduce, as opposed to be just a clump of particles, right? How do you define that this is an individual? This is already very hard, okay? And we think, I mean, intuitively, you kind of know, right? If you look under a microscope, you see some bacteria and some cells, you say, okay, this is one bacterium, this is one thing, and then this is one cell, this is one thing. But often it gets really blurred. Okay, so for example, you have some things which are slimes, for example. It's a bunch. Sometimes it's even unicellular. I'm not sure. People in life sciences might correct me. But so you have this thing which can span like super huge distances. Do you define it as one thing or as a collection of things collaborating? Same thing for our body. Okay, can you say that the individual is the individual cell on my skin, or it's more accurate to say, okay, the individual is the human, and then it's composed of different cells, etc. So this is already a very hard question and very important question, because when you will see when we do the models inside our computer, we have this clump of particles that move together. Can you say confidently that this is one thing, one creature, or is just a bunch of particles collaborating? Okay, so this is the first very hard thing to do. Then the other question is concerning evolution. So in many definitions of life, you need some sort of evolution. So you can think it as Darwinian evolution, for example. So it could be Darwinian evolution, but not necessarily. Okay. So for example, if you look, il y a des chaises dehors aussi, si tu veux. So for example, if you look at humans today, okay, we're still evolving technologically, okay? We are acquiring much more tools, etc., becoming more advanced. This also could qualify as evolution. So there is this question. Usually in the definition of life, you have some sort of evolution, meaning some sort of way to change and adapt to the environment. And usually this evolution, we define it as open-ended. And this means that it is some evolutionary dynamics that creates ever-increasing complexity in the entities that you have, okay? So meaning that, for example, on Earth, you started with something very simple, unicellular organism, etc. And as you go on in evolution, it becomes more and more complex, then you develop intelligence for humans, etc. And so this quest of open-ended evolution is, okay, the question is, do you need such a thing for life? Most people would say yes. And the second question is, how do you get this thing? Because we'll see that in most models, I would say even all models that we have, artificial simulations, you can set up some kind of evolution, but very quickly it stabilizes. Okay, you have some predator and prey, they evolve, they become better, and at some point they just stabilize. No more complexity, they don't evolve super advanced strategies. So yeah, so the quest for open-ended evolution is another very big question. And then of course, yeah, so do you need reproduction for life? Most people will say yes. But you could also think of systems where the system never reproduces, it just becomes more and more complex. It's able to adapt to the environment, etc. So this is another question. And okay, when you manage to land on a definition of life or something, then the next question to ask is life standard or expected? Okay. In my world model, is it usual, common for life to happen, or is it a very specific, rare scenario? Okay, so this is another very big question. And if you're able to answer this question, you should be able to say also, okay, I'm fairly confident that aliens exist because I've shown in some sense that life is extremely expected. Or you could say also the opposite. You can show maybe you can show in some way that life is extremely unexpected with some models, and so that you should not expect really aliens to be there. And of course, related to this, okay, what are, if any, the necessary or sufficient conditions for life to arise? Can you identify them? And then, okay, if you have these conditions, you can look how rare are these conditions to know how rare is life. So this is the first big question: how does life arise from the non-living? And then the other questions that was outlined in this paper is, what are the potentials and limits of living systems? So the first question is, okay, how far does open-ended evolution go? Because we define open-ended evolution as evolutions that drives complexity ever increasing, but maybe there is a moment where this complexity stops increasing, right? So how far does open-ended evolution go? And the other question that I really like is, are there predictable trajectories in evolution? So if, let's say, I seed, I don't know, Mars with some bacteria in some puddle of water that is there, do we expect more or less the same strategies to appear on Mars? Right? So for example, one strategy which seems to be like kind of a very good strategy for evolution is intelligence, right? In general, if you are more intelligent, you will be more adaptable to your environment. So the question is, are there any trajectories which you can predict in evolution? Because it feels very chaotic, but maybe there are some attractors. Okay. And the last big question that was asked in this field, which is kind of, we won't touch this too much on this course, is how is life related to mind, machines, and cultures? So this is really the question of artificial intelligence, whether you can have actual intelligence or consciousness in computers or other artificial life forms. And then the questions of ethics, etc. So if you build actually artificial life in your computer, is it actually unethical to just turn off the computer and stuff like that? So yeah. So these questions we won't touch too much, mainly because, okay, we're not there yet creating life in the computer, so it should be. Although there are some advances in machine learning recently that may challenge this question. Okay, so this is kind of the very broad questions of artificial life. And now we'll have a look kind of chronologically at what people did in this field. So are there any questions until now? Okay, good. So the history. So let's start first in very ancient times. So this is just to show like the drive of the human to try and create synthetic life. So one very common example is in alchemy, where you have one of the main goals of alchemy was to create homunculi. So alchemists thought at least that if you combine the right set of elements, you could actually create a small human or a small living creatures. Okay. And so here I pasted a homunculus recipe from the 1500s. So you see it's quite involved. So I'll read it to you. So that the sperm of a man be petrified by itself in a sealed cucurbit, I'm not sure what is that, for 40 days with the highest degrees of putrefaction in a venter equinus. And that is actually a very common ingredient, apparently, in alchemy. And so it is fermenting horse dung. Okay.
Cucurbit's like a pumpkin.
Cucurbit, yeah, maybe a concombre, cucumber, yeah. And so this venter equinus, so they have this term, is this fermenting horse dung. And I think it's very common ingredient in alchemy because essentially what they notice is that you get this horse dung and then it automatically becomes warm for like 10 days because of the chemical reaction going on. So they thought it was very important. So if you combine this with human sperm and then you wait, basically, it says that after this time it will look somewhat like a man, but transparent without a body. If after this it be fed wisely with the arcanum of human blood, not sure what is that, and be nourished for up to 40 weeks and be kept in the even heat of the venter equinus, a living human child grows therefrom with all its members like another child which is born of a woman, but much smaller. Okay, so this is, it fits very well artificial life. Okay, they just wanted to create some life form using some chemical ingredients. And later we'll see that artificial life kind of separates into three approaches, one of which is kind of the chemistry and biological engineering, which is kind of what they were trying to do. Okay, so if you advance, no, actually, if you go back a bit more, you have this notion about, about automata. robots. And so automata were another instance where humans were trying to replicate real life, but this times mechanically. Okay, and so apparently some of the first mentions of mechanical automata were already in 200 before Christ from Hieron of Alexandria, and which apparently made a mechanical play, so a theater play, composed of machines which were operated by pulleys. So yeah, so like most fields of science, artificial life was also invented by the Greeks, it seems. Yeah. That's good to know. And then later you have all sorts of other automata. So you have this Al-Jazari's music playing automata. So it's not really clear that they are automata in these depictions, but apparently using hydraulics, he was able to make music with these kind of robots. And then there was Da Vinci, which designed this armored knight, which was driven by pulleys and cogs, and that could move. And another very interesting automaton was Jacques de Vaucanson artificial duck, which was in the 1700s. And this was claimed to be a robot duck, which you could feed, and it would actually poop, digest, and poop out what you feed it. So this is some recreation of this this automatic duck, but actually it was fake. Okay, it was, let's say, it was preloaded with duck poop, and when you fed it, it activated a mechanism that executed it. But until then, we made much progress. So if you look up Cloaca, it's an actual robot that digests. If you want to see the modern version of this artificial duck. Okay, so this is all to say that this artificial life, this drive to try and recreate life, it dates back from quite a while. And okay, so now we go to the 1940s, where the actual things that we will cover in the course start. Okay. And this starts actually with von Neumann in the 1940s, okay? And the question that von Neumann was asking is, he asked himself, what does it take to build a self-replicating machine, okay? So people see that in nature you have self-replication everywhere, okay? Every animal and plant is doing it. And the goal of von Neumann was to try and understand, kind of motivated by the fact that some people thought that biological animals, etc., are just meat machines in some sense. And so von Neumann wanted to understand self-replications, but in an actual machine, okay? And then later on, actually, people took this idea as one of the main, let's say, one of the most realistic ways to colonize space with what we will call von Neumann probes. And I will explain what is that later. But essentially, it's the idea that if you want to create a base on the moon, it's very hard to do, right? Because you have to send a lot of materials, a lot of robots there to build. So of course, if you can create a self-replicating robot, you just send a single robot to the moon, and then it will just use the parts that it finds on the moon to make a second copy of it. And then you can make a whole colony by just sending a single robot. And so this seems like super science fiction, and it actually is. But in 2004, there was actually a study supported by NASA to consider the feasibility of something like this. So this is just a artist depiction of such a base where you have like a part for assembly, a part for part fabrication, chemical processing, and then you have solar panels for energy. And this is supposed to represent a self-replicating base. And so this was considered by NASA for actually space colonization. Okay, it didn't bear fruit, but it was considered. And okay, so when von Neumann first asked himself its question, it considered this thing called the kinematic self-replicator, which is a very high-level, let's say, machine to understand how self-replication works. So you have the replicator, which is either a creature or a robot, and you have to imagine it as floating in a sea of parts, okay? And the robot itself is composed of these elementary building blocks that floats in the sea. And so in this way, it's very easy to see how it could replicate itself, at least in a high-level sense. So it has some sensory organs, so it can see what parts float in front of him. And then he has a grabbing organ that can just grab the part and assemble it. And so the way it self-replicates is quite easy. It's just that it stands there, look at the current. Whenever there is a part he needs, he grabs them, assembles it, and thus it just assembles a copy of itself. Okay, so this is a general procedure. And yeah, so this is an artist depiction of this. So you have here, it's even easier. The parts are assembled in a shelf. And you have the first robot, which picks the part, constructs the second robot, also has an arm to giving the parts. And then you can go on and construct a full army of robots in this way. And then there is this very interesting thing. So this was, so I forget his first name, but the father of Roger Penrose, the famous physicist. He actually designed an actual implementation. Let me remove the sound. So let me go to the more impressive ones. Right here. So he created these wooden robots. So you have to think of the wooden robots as the elementary parts. And as they move together, they can interlock to form this double robot. And if you put a third robot, okay, it releases the other one. Okay, so this is the first step. So this is not self-reproducing yet. But if you change a bit the mechanism, so here they explain, let's see. Right. So now you have a robot where it can assemble into 3 parts. And then when a 4th part comes in, okay, it separates and creates 2 robots. Okay, so this is exactly the kinematic self-replicator and examples. So if you get a sea of these robots, or you put them on a table and start vibrating the table, some robots will assemble, and then they will assemble more robots, and this will create an army of these two wooden pieces robots. Okay, so that's something very cool that was made by the father of Roger Penrose, who I forget the name. So this is an example of this mechanical self-replication. Okay, so this is very nice, but theoretically it's not very satisfying. Okay, because when we say that you have this sea of parts, you think these parts are very high level. Okay, for example, oh, I saw one arm, I saw a motor, etc. So this is not very satisfying because you have these very high level parts, whereas in nature we don't think of having access to very high level parts, right? If you start with the Earth before life appeared, you have some molecules, and that's pretty much it. You don't have something that can sense light and you can just put it as an eye. So if you have a sea with very high level parts, the replication seems almost trivial, but it's not very interesting because you have these high level parts. And now if you say, okay, let's try it with a sea of low level parts, then it becomes much harder to describe because you must say how to combine these low level parts into high level parts, which is very hard. And then there is also a paradox that we'll revisit in the next course, is the question of, is it even possible? Okay, because you might say that, okay, if you have a machine that will build a copy of itself, it should have a blueprint of itself, right? So, okay, that's good. Then it uses the blueprint to produce a copy. But then if the copy of the machine should be able to also copy itself, it should also have a blueprint of the machine, right? So you not only need to copy the machine, you need to copy the blueprint. So you need a blueprint for the blueprint. But then the blueprint of the blueprint should also be copied, and so on and so forth. And so it seems to be a paradox. Okay, you can never create something as complicated as yourself because you need the blueprint of the blueprint of the blueprint. Okay, of course, this is a fake paradox because we are doing self-replication, so it must work some way. And but von Neumann wanted to actually formalize this and understand how this paradox somehow is solved. Right? So so what von Neumann did is that he used some ideas from Turing machines and computability, which we'll visit in the course. And he was actually able to prove the existence of such a self-replicating machine in a very controlled environment. So a physical model that he made. And the very, so let me just comment on Turing completeness for people who might not be familiar with it. We will define it more precisely in the course, but roughly what it means for a system or a programming language to be Turing complete, it just means that it can emulate the same programs that C++ or Python or any other language you can think of. Okay. So if I have a physical system that is Turing complete, what it roughly means is that you can build a computer inside it, and this computer can run any program that you could run with C++, for example. Okay. And this can be made very precise, and it's very impressive as a result, but we'll see it in the course. So he based his ideas really on this. And the actual construction of the machine, which we'll actually see in practice, is basically this thing. So you have a tape, and the tape is the sort of blueprint. Okay. Then you have a tape reader, which reads the blueprint, and this tape reader controls a construction arm, which it uses to duplicate himself. Okay. And the idea is, of course, that you need to duplicate the tape reader, the construction arm, as well as the tape. Okay. And so here again we see the paradox. Okay, we need to describe the tape on the tape, but if I describe the tape on the tape, then I need more tape, and then I need to describe more stuff, and it seems like a paradox, but it's not. Okay, so this is an actual implementation of this von Neumann machine, and the way he did it is like he designed a very simple physical world, which we'll call a cellular automaton, which we'll define, and inside it he proved that he could build this machine. Okay. And so the solution to the paradox, if you want, in one phrase, is simply, you don't need a blueprint of the blueprint. The blueprint itself is a blueprint for the blueprint. Okay, I don't know if it's clear, but essentially it's just, you don't need to describe the tape on the tape. Just copy the tape, right? That's it. You don't need to describe the blueprint, just put it in a photocopier and hand the blueprint, right? This is essentially the solution. Okay, any questions so far? I know this is historical, there's not much technical stuff, but okay, very good. So yeah, so something which is very interesting is that we'll see that this idea of self-reproduction, etc., is very closely linked from this idea of Turing completeness, of the fact that you can compute any program. And I feel this is very surprising. Okay, I would never have thought that something like life was very connected to something like theoretical computer science, but it actually is, very much. Yeah, so this I already mentioned. So to put this idea to the test, von Neumann with Stanislaw Ulam developed the first cellular automaton. And so a cellular automaton, you probably already heard of it, is simply a simulated world which is composed of an infinite grid. Okay, so just squares. And each square on this grid can be in a finite set of states. Okay. So this is an example of a configuration. So the grid is not pictured, but you have this infinite grid, and then you have different states here represented by blue arrows, red arrows, and this green losange. Right, and then the other property of the cellular automaton is that the physics of the cellular automaton, how does it evolve in time, is simply that states interact with very simple rules only with their neighbors. Okay, for example, if your neighbor is a red arrow, then in the next time step I will also become a red arrow, for example. Okay, and so yeah, so you might know the most famous example, which we also talk about, is the Conway's game of life. Okay, this is the most famous example of a cellular automaton. And okay, so this is an example of von Neumann cellular automaton. So this is a very strange machine that just builds this train of red arrows. And this will be the subject of the first course. So we'll learn how this automaton is defined and how you can use this to actually build a self-replicating machine. All right. So, okay, closely also about at the same time, a bit later, using von Neumann's idea, it was Niels Baricelli, which is not very well known as a scientist, but he actually was the first one to do a computer simulation of an artificial life system. Okay, all the work of von Neumann was pen and paper. So he designed this thing, and if you wanted to simulate it, you just had to draw by hand each step. Okay, so it was very tedious. And so this guy, Niels Baricelli, was the first one to actually do a computer simulation. Of course, this was also very slow. So you would launch the program the night before, And after one day, you would come back and see the results. And if you made a mistake in your code, well, you have to wait for one more day. And yeah, so he implemented this cellular automaton, which is called the Baricelli cellular automaton, which we also see, and which looks like this. You might have seen it already on the website. So this cellular automaton is a one-dimensional cellular automaton. So the full state is specified here on top. Different colors are different species. And then as I let it evolve, we see the history of this cellular automaton. So time is going downwards. And so you can see that there are some colors that become dominant, okay? And this can be interpreted as some creatures evolving and being more adapted, and so taking up all this space. So if you wait enough, as you can see, here you get a few species that survive the initial condition, okay? Here I don't describe how it works, but we'll see it during the course. Very good. So in parallel, kind of a bit later, there is Alan Turing, another big guy of computer science, of course, introduces these reaction diffusion models in this paper. And so these reaction diffusion models essentially try to explain the goal. One of the goals of these, try to explain how can you have some patterns that form from a continuous system. So for example, if you have a tiger or a leopard, their fur has like discrete dots, but of course the underlying system, like the cells in the skins, are almost continuous. So how do you get these discrete dots from a continuous system? And so implemented these reaction diffusion models, which basically model it's some differential equations that model some chemical, how do you say, some chemicals that interact. And I don't know if, probably he did some simulation also at the time, but it gives things like that, which are very beautiful. So here the system is completely continuous, the underlying system. But as you can see, as you let the dynamics evolve, it forms these sorts of dots, okay? And then you can have different parameters to form different shapes. So this looks a bit more like the zebra stripes, for example. And then what else do we have? Yeah, this is more dots. And okay, so this is a continuous system. So it's kind of a completely different approach from the cellular automaton approach, which is completely discrete. But it's one way in which we can explain how do you have the rise of discrete dynamics from actually a continuous system, an underlying continuous system. Okay. And actually people have shown that these reaction diffusion models, they describe very well a lot of patterns that you see in nature. So this is for shells. So you see this is an actual picture of an actual shell. And this is a picture of a simulated shell that has been obtained by applying a reaction diffusion equation to the dynamics of the growth of the shell. And as you can see, it models it perfectly. Okay, so we think that it's actually what's happening. The actual differential equation describing the chemicals on these shells are described by the reaction diffusion. Another example is zebrafish, which can have different patterns on their skin. And they're also a typical example where you can explain the patterns very well with reaction diffusion models. Okay, so this was the very beginning of artificial life, okay, with von Neumann and Alan Turing. And then from the 40s until the 70s, I think not much happened. I couldn't find much stuff. Probably something happened, but in the 70s, there was this big thing, which was the introduction of Conway's game of life, which you probably know. And so this, again, a two-dimensional cellular automaton, which has only two states. So each pixel that you see, each grid plan can be either on or off, or you could say alive or dead. And it has very simple evolution rules. So compared to the cellular automaton that von Neumann introduced, which had 29 states, it's much, much simpler. And the kind of thing you can get with this game of life is very, very intricate. So here we see what's called a glider gun. So it's a configuration that as you evolve it, it generates those little gliders indefinitely, okay? So this is not quite reproduction, okay? It's not reproducing itself, but it's generating these gliders, okay? And people have been crazy about this model, like they've invented some really crazy stuff, which we'll touch upon also. And around this time also, so there is Burks that takes the works of von Neumann, which was kind of incomplete, and completes it. So actually shows that you can have a self-replicator, let's say, more completely, because it was at the end of von Neumann's life that he was doing this stuff. And he also founds the only group that actually works on artificial life at the time. Okay, at the time, the word artificial life did not exist yet, but Burks had a group, I don't remember where it was, I think at Princeton, but I'm not so sure, which was working on artificial life. And around this time, there are some theoretical results that come out about cellular automaton, about reversibility, which we will also talk about. Okay. So then in the 80s, that's where really it starts to pick up. So we have this guy, Christopher Langton, which again starts performing the first actual simulations of cellular automaton on computers, because computers are getting more and more powerful with ideas from von Neumann. And he is the guy who coins the term artificial life, okay? So he's the founder of the field from that point of view, even though you could also argue that von Neumann is the founder of the field. And he's working in Burke's group, precisely. So here he talks about artificial life in this way. So let me read you the quote. So artificial life is the study of artificial systems that exhibit behavior characteristic of natural living systems. So we have this idea as life as it could be. It is the quest to explain life in any of its possible manifestations without restriction to the particular examples that have evolved on Earth. This includes biological and chemical experiments, computer simulations, and purely theoretical endeavors. So this is what I was talking about, the different pillars or approaches of artificial life, where you have biology, chemistry, then physics, robotics, and then purely theoretical math. Processes occurring on molecular, social, and evolutionary scales are subject to investigation. The ultimate goal is to extract the logical form of living systems. So really this idea to extract the essence of what is life in an abstract way. And he also made some very nice cellular automata. The first one is Langton ant. And so this cellular automaton is very simple. So you start with an ant, which is this red dot. And this ant has some rules on how it moves. So for example, if it's on a white square, it will move left and paint the square black. If it's on a black square, it will move right and paint the square white, and so on and so forth. And then you can also condition from what direction it arrives, etc. When you start to simulate it, it creates some very beautiful stuff. You can have some very crazy figures that appear. It feels very chaotic, okay? So you have very simple rules, but it goes on for very, very long before at some point it stabilizes and creates some sort of highway. And this, I think there are some theorems on when this highway is produced. So these are examples with more states, so more colors that the ant can color the graph. And it's very cool to look at. So almost always it finishes in a highway. There are some theorems about that. I'm not sure what they are. So this is sped up considerably. So this was also invented by Christopher Langton. So this is one which covers completely. Right. And then let me show this and then we'll do the pause. So we have Langton loops. And this is kind of the spiritual successor to von Neumann's cellular automaton. So it was first modified by this guy, Cod. And then it was further modified by Langton. And they ended up with this cellular automaton, which is very simple. So you have these loops that contain some stuff that circles around. And this stuff escapes and create a neighboring loop. And then the process restarts. So here we really have self-reproduction, okay? And in that case, it's very interesting because this cellular automaton is not Turing complete, as we said. Okay, so it's some different approach, let's say. But so this is one example of self-reproduction in an artificial system. And then people modified it even more. They added the possibility for genetic variations. So you have loops of different sizes, etc. But this is very similar to what von Neumann wanted to do, but drastically simplified. Okay, so you have these loops that propagate indefinitely. Yes?
So why is this not Turing complete then?
So actually people have shown, so if you have Turing completeness, you can show that you necessarily have some sort of self-reproduction, but you don't need Turing completeness for self-reproduction. So you can have it without Turing completeness. In that case, people have shown that this model is not Turing complete. But we'll visit this. It's actually a very subtle question. Yeah. So let me end with this, and then we do a 15 minutes pause. So there was Langton introduced these ideas of three types of a life. So the first one is soft a life, which is based on computer simulation, virtual systems. Okay, trying to find life in these virtual simulated systems. Then you have the so-called hard a life, hardware, which is more like robotics, actual mechanical systems, automata. And then the last one is wet a life, and this is like the chemical systems or bioengineering, etc. So all this research. So in this course, we'll focus mostly on soft a life. Okay, that's what's easier to do in a course. And I'm not very good with experiments, but there are people working on all of these fronts, and all of the fronts are very interesting. Okay, so now we should do a pause of 15 minutes, and we'll restart at 3:15.
Yeah, so I think it means that, like, okay, I think it means that in principle, if you open like a Python shell, you could code Python again. I think.
All right, guys, let's restart. So, okay, we left off about the three directions of a life. We were about in the 70s, 80s. And so in 1982, there was Wolfram. So you might know Wolfram from Wolfram Alpha or Mathematica, the guy who made those things. So in 1982, he was interested in the study of cellular automata, in kind of not completely rigorous, but a more rigorous theoretical study. And so he studied the even simpler than the game of life, let's say. He studied the one-dimensional cellular automata. Okay, so let me describe them really quickly. So since they are one-dimensional, they are described by, the whole world is a single line, of course. And it's a cellular automata, so it's divided into grids, in a grid. And each state is the same. The state can be either alive or dead, or if you want, on or off. So here you have two colors, black and white, to denote the two states. And then you describe a rule for evolution. So given a state of the world at time, let's say t equals 0, how do you get to the state of the world at time t equal 1? And so this is an example of a rule. And so you need to specify, So this cellular automaton interact. We said that cellular automata usually have rules where they interact only with their neighbors, okay? So if I pick some random square, let's say this one, the black one here, its state in the next iteration will depend only on its two neighbors, okay? So if I want to define the evolution rules, or I will also say the physics of this world, I just have to specify what happens for each triplet of states, right? So for example, if I have a black state surrounded by two other black states, it will become a white one, and so on and so forth, right? So for example, here, if I have three white states or empty states, in that case, it remains white. And then what you do to simulate the dynamics of the automaton is just you scan here over all the triplets, you look at your set of rules, and you determine the next state. So here, what's happening here is that we are computing the next time step for this automaton. And then what we're interested in studying is how the properties of these dynamics. So you simulate the automaton, you draw all the different states and see what happens, okay? So here we have a relatively small set of possible rules, okay? We have 255 different possible rules, okay? Can anybody tell me how do I get this number for the number of possible rules for this automata?
Why not 16? Why not 2 to the power of 4? Because you have three states that describe the one cell is you and the
Right.
universe and then one.
Yes.
Why not 2 to the power of 4?
Okay, so the question is why not 2 to the power 4? So the way I get this number is that you have 8 possible configurations of 3 cells, okay? And for each one of those, you must specify if in the next time step you're black or white, okay? So you need to choose 2 for this one, 2 for this one, 2 for this one, so 2 to the 8, okay? So in practice, it's actually less than 2 to the 8. So for example, if I give you a rule and then you just flip the colors, black goes to white and white goes to black, it's technically a different rule, but all you did is just invert the colors, okay? So in some ways, these 2 rules are the same. So I have in principle 255 rules, but in actuality it's less than that because of the symmetries.
Technically, 2 to the 8 is not 255.
Oh, whoops, 256. Yeah, sorry. That's correct, yeah.
But if you just flip the colors and it's the same thing, shouldn't it be 2 to the 7?
Yeah, so not exactly because some rules are symmetric. So if you flip the color, you get the same rule. So it's not as simple as that. The question was, shouldn't we have 2 to the 7 because of the color flip? But actually, yeah. So there was a question back there, I think. Yes. Yes. So the question was, is there a symmetry between the flip of the direction? And the answer is yes. Okay. You have some rule, for example, that makes all the stuff go to the right. If I do symmetry where I flip the rule like this, everything will go to the left. It's technically a different rules, but the dynamics are the same. So depending on what you consider as symmetry, you have much less actually than 256 rules. Yeah, so Wolfram, what he did is essentially he studied almost individually these set of rules. And what he found, or at least what he conjectures, is that these rules can be classified into 4 classes. I prefer to say 3 classes actually, but he said 4. So the first class is the rules for which you get very quickly homogeneous behavior. So for example, I start with half black, half white cells, and then after 2 or 3 steps, everything is white, for example. Okay, you can find such a rule. For example, if I decide that any of these states go to the white cell, I will just erase everything and then remain white, right? So this is the first class, which is arguably not very interesting.
So the tape is finite and the
No, so
thing loops.
so it depends. So you can either consider infinite tapes, but usually this is hard to simulate. Or what you do usually is consider a tape where only a finite number of cells are non-white. You kind of define a ground state, so with this 0, where all white goes to white. But often what you do is also either you use a finite tape or a tape that loops, right? Periodic boundary conditions, so that this cell here is close to this one, right? But for Wolfram, we're considering like a finite tape, actually. Yeah. So the second class we have is quickly stable or periodic behavior. So not something that erases the initial conditions, but something that becomes very predictable after a few steps. So for example, something that goes from black to white, black to white, black to white. Super easy to predict.
So
Yes, another
if you
question.
consider a finite tape, then
Mhm.
isn't it obvious that you
Yes.
always have a periodic?
Yes. So the question is, if we have a finite tape, we always have eventually a periodic behavior because we have a finite set of possible tapes. So you necessarily go back to a previous tape. And that's correct. So when we say stable or periodic behavior is that it should happen quickly. So like after a relatively slow amount of steps. Okay. These classes are not at all defined rigorously. In fact, if you try to define them rigorously, you find that they are not computable. You cannot tell which class is in which. So, but the idea is that very quickly it becomes periodic. Then you have class number 3, which is kind of chaotic behavior. And here what we mean by chaotic behavior is essentially the intuitive thing. When you look at the dynamics, it looks random, okay? It looks like white noise or something which is really unpredictable. You don't see any order appearing. But it's not the chaos of physics where you have like For an infinitesimal perturbation, then you have an exponential separation. It's not in this sense because you cannot even do an infinitesimal perturbation since it's a discrete model. But okay, chaotic behavior, just bear in mind, it's just random stuff happening. It seems random, although it's not, right? Everything is completely deterministic. And then class number 4 is the class which is none of the above. And this is the actually conjectured to be, by Wolfram, the interesting class. Okay, so you have something which is kind of in between chaos and periodicity. So in between complete unpredictability and complete predictability. And you have this idea that when you have the edge between the two, then you can have some complex behavior emerging. This was kind of the idea of Wolfram. So here are some examples. So here what I show you is the history of this one-dimensional automaton. Okay, so the initial state is up there, and as you go down is how it evolves. Okay, so the first row is examples where we start with a tape with a single black dot. Okay, whereas the example below is different rules. Everything is different rules. Is when we start with a tape which is randomly initialized with black and white. So here we can notice the classes of Wolfram. Okay, so this one here would say it's probably the periodic class. Okay, this is very predictable. What happens next? If you have an infinite tape, it's not really periodic because it's growing, but it's very predictable what will happen next, right? You know what will happen next. This one is kind of the same. This one is kind of interesting because it is very predictable. Okay, what will happen next, but it's not really periodic, right? It has this fractal property. But this also falls into class 2, okay? And then we have this one. And this, if I remember correctly, I don't remember which rule it is, but I think this is one of the rules which is, I'm not sure. I'm not sure if it's a chaotic one or an actually class 4. In between the two, I think it's a chaotic one because you have these triangles. It's very hard to tell when it will be a small or a big triangle, so it's kind of chaotic. And then in this example, so this one, I'm pretty sure this one is one which is class number 4. Okay, so you see it's not entirely predictable, but you can see emerging some structure. Okay, you have these lines of triangles, and then I don't know if you can see. Yeah, you can probably see it. You have these lines, these vertical lines also emerging. So these resemble kind of gliders, right? So these triangles, they are gliding along. So with this, you can actually compute stuff. People have shown that it's Turing complete. So this one is another chaotic one. This one as well, and this one as well. Okay. So you see what we mean by chaotic is like, okay, at least intuitively, you see at a glance, I don't see anything special out of it. I have no idea what will happen in the next frame. Whereas here, if I ask you, you would say, okay, probably this thing will continue down. Maybe when it collide with a vertical one, it made some problems, but okay, you get the idea. So what Wolfram did is that it conjectures that whenever you are in class 4, you are automatically computationally universal. So this Turing completeness again. So yeah, that's quite a strong claim. And it was proved, actually now it's proved for more than a rule. So it's rule 110. There is a way to give a number to these rules, and it's this one. And this rule was actually proved to be Turing complete in some sense, so that you can prepare the initial state in some way such that these gliders, they collide and somehow they compute for you an answer in the end. You can interpret the answer. Yes, question? Okay. So the question is, why did I say that there should be only 3 classes? It's because for me, class 1 and 2, they fall in the same idea where the dynamics are very predictable very quickly. Whereas they completely raise the initial conditions or not, it's not particularly interesting. That's why. So class 2 and class 1, you can put them in the same class. It's super predictable dynamics, essentially. Right. So even with these very simple automata, okay, so we started with von Neumann, which was 2-dimensional, 29 different states, and then you could build a computer inside that. And here we have arguably one of the simplest way you could think. So just 2 states and just 1 dimension. You can still build some sort of computer inside that. And we'll see that during the course. Okay. So then there are other applications of cellular automata, for example, in physics. So one of the main example of this is the so-called lattice gas models, where these lattice gas models is essentially some cellular automata that attempt to simulate some perfect gas dynamics. So you have this intuition that you have a perfect gas. You can model it as some balls going around in space in a straight line, and then when they hit another ball, they just scatter. And then if you put enough of these particles, you get a gas at large scale. And so this is exactly that, but you do it on a cellular automaton. So instead of having some particles that can move anywhere continuously, you have a grid, and then the particles can take some precise directions. And then if two particles end up in the same location, they scatter. So these are lattice gas models, and they were actually in the beginning of the computer. So I think here we are now in the 80s. People thought that maybe this would be a very good way to solve or to simulate Navier-Stokes, right? Instead of actually solving the differential equations, you use the microscopic model and then you recover the fluid dynamics as you put many particles. And actually it kind of works. So you can show that if you prepare your lattice gas model well enough, with enough rotational symmetry, you can actually show that at large scale, large grid, you recover Navier-Stokes equations, dynamics. So here is an example. So the definition of this video is not great, but here we have an example with just 4 particles in this lattice gas. They are represented by these arrows. The arrow is just the direction in which the particle goes. And you will see when 2 particles collide, yeah, it's not very clear, it's a bit too fast. But when 2 particles collide like this, they exchange their momenta and they go away like this. Okay, so this is a momentum conservating collision. And so you have that, you start with that. And if you scale it up, so this video will be not very clear because it's very noisy, but okay, here we have an initial configuration, and the whiteness of the picture is whiter the more particles you have. So it's kind of the density. Okay, so here I start with some random noise of particles in all directions with a huge overdensity in the middle. Okay, so if you think about this, like a gas, it should kind of create an explosion. Okay, they should make a wave in where you have the concentrated particles. And so this is the lattice gas. Okay, so as you can see, it kind of looks like a wave is moving away. Behind the wave, there is some sort of depression. And okay, now it's kind of hard to tell, but you still have waves traveling in this mess. So if you average this and you look at the density, this case, it doesn't follow Navier-Stokes because we have only the 4 directions. But if you add more direction, it does. So this is a lattice gas. So these are another use of cellular automaton, which now it's completely deprecated. Okay, now simulating the differential equation is much faster than actually simulating millions of particles, but it was something that people considered. Another example of this, it's not quite a cellular automaton, it's some kind of artificial life systems, is boids. So the nomenclature for boids, it's actually bird-oid objects. So something like a bird. It's created in 1986, and it's a program which simulates bird flocking. Okay, so you have these individual birds, and you put very simple rules. So a bird wants to align with the center of mass of the neighboring birds, or the direction of the neighboring birds, and it wants to escape birds which are too close. Okay, and if you actually simulate this, it gives this sort of dynamics. Oops. Right. So here, each bird is acting individually according to its own rules, but we see that we have an emergence, naturally, of self-organization. Okay, they form these flocks, and so you have 2 flocks. When they collide, they kind of interact. Some birds are stolen, some are given, but it's very, very simple rules give rise to this very complicated behavior. Okay. And so, yeah, so models like this, for example, they might be used to compare or like make a hypothesis. Okay, you see bird flocking in real life, and you cook up this simple model and you compare the dynamics to the actual bird flocking. And this can give you an idea, okay, how do birds actually do flocking, right? How do they do it? And in this case, it's very simple. Each bird looks at like the neighbors in a 1 meter radius, and it tries to align with them while trying to avoid being too close to some bird. And that's it. So here we have another use of some like alive simulations, which is for computer graphics. Okay, you can see that these kinds of board simulations are used very often in video games, for example, when you have to simulate flock of birds or flock of fish. And so also sometimes you use some of these like computer simulations as problem-solving algorithms. Okay, if you know, the most common example is the ant colony optimization, which is a heuristic algorithm to find the shortest path between 2 points on a map. And essentially what you do is just simulate some ants that want to go from point A to point B. The ants lay down some pheromones such that they are more likely, I mean, when they find the goal, they mark the spots. And then what you see is that more often than not, the ants automatically find the shortest path. So you can use this also for some algorithms. So generally, one point that I want to make is that artificial life and very nice visualizations for the systems are very closely linked, okay, still today. So there are many people who are doing artificial life, just these very simple systems, because they produce very beautiful visualizations which are completely unexpected. Like you have this emergence of complexity which is completely unexpected. So this is a big part of people working in A-Life today, which is not from the A-Life point of view, just from the point of view of creating some beautiful visualizations. And okay, so this is for the 80s. And now we get into the 90s. So in the 90s, we start to have more and more personal computing. Okay, computers are becoming more and more common. And so this allows for much more simulations. And we also see that there is less theory than before. And in this case in particular, there is a huge, huge focus, I mean, from what I saw at least, on the game of life. And this goes on well into the 2000s, okay? So I think I should have made a poll for who heard of the game of life before, but I'm sure it's more than 80%. And so people are just crazy about this system. So this is mostly done from amateurs, right? It's not people doing research, just people doing this for fun. And the people found like millions, okay, maybe not millions, but thousands of different creatures, like still lives, so things that are just like plants, let's say, that don't move, then gliders, oscillators, and all crazy stuff. And so this is just a very nice simulation that I want to show you really quickly. So this culminated in people actually making computers inside the game of life. And of course, it's clear that if you have a computer, you can simulate the game of life on this computer, right? That's what the program is. So the question is, if I can make a computer in the game of life, I should be able to simulate the game of life inside the game of life, right? That's just natural conclusion. And actually people did that, exactly that. So here you see, so these are some game of life dynamics. Here we are quite zoomed in. It's not clear what's happening. Okay, but as we zoom out, okay, we see that there are some squares, there are some highways here. Some information is being exchanged, it's not clear. If we zoom out more, we see that, okay, there is some cells with information going around them. And if we zoom more and more, then you start to see that, okay, there are some white cells and some black cells. And if you continue zooming out, okay, yeah, well, you're at the starting point, okay? So here, really, this cell is being, it takes a lot of time, right? If you see the things going around, they're going around many times. So essentially what they're doing is like they're looking at the neighbors to compute what the next state should be. And once this is computed, it actually performs the change and the square change according to the game of life rules, right? And so this is a very nice website. It's fake, of course, but you can zoom out and it's game of life all the way, right? So this is one of the very cool things of Turing completeness, where you show that it's Turing complete. You can build a computer inside it. The system itself is built on a computer, then I should build the system inside the system, okay? This is some kind of very esoteric self-reproduction, okay? It's even more strange than self-reproduction because you're reproducing the physics of your world inside your world, okay? But okay, so just to say that people really found crazy stuff in the game of life, the amount of research that went into this is crazy. And so what we learned from this is that the game of life seems to be a very special set of rules, right? So I didn't describe the rules for the game of life, but the matter of the fact is that, so in 2D, if you compare to the 1D, so in 1D we have 256 rules. In 2D, you have something like in the 250,000 if you restrict yourself to the rotationally invariant rule. And the game of life is just one of them, right? So it's already impressive that it was found, essentially, it was the first rule that was found among this set of rules. And it seems to be the most interesting, right? People have searched a lot in these other rules. They found some interesting stuff, not as good as the game of life. So it's very special, but it also has a lot of drawbacks. So it's really not the ideal artificial life systems. Okay. Some main problems is that you don't really have spontaneous emergence of very interesting stuff. So if you start with a game of life world, you initialize the cells randomly and you evolve it, you will get some interesting stuff. You will get some gliders, some oscillators, some a bit bigger machines, but you're unlikely to find some really big machine that self-reproduces or something like that, okay? So in some sense, you don't really have this, or at least not at the scales we considered. You don't have this spontaneous emergence at reasonable scales, okay? All this crazy stuff that you have in the game of life has been a product of intelligent design, right? People have put the cells exactly where they need. The second problem, which is also related, is that the dynamics are very brittle. So what I mean by this is that you take the program I showed you before, you just change a single cell somewhere, it will break everything. Okay, it's completely dependent on each cell being exactly what it is. And so if you have extremely brittle dynamics like this, it seems very hard to have something like evolution, right? You cannot have a mutation because any mutation will almost always destroy you completely. And so that's also related to the first point, right? If you want to get really complex stuff spontaneously, it kind of feels like you need some sort of mechanism to increase complexity. And that's usually something like evolution. But without mutations, it's very hard to have. Yeah, and the last stuff is also related, is that it's completely discrete. So you cannot do a small change, right? The smallest change you can do is flipping a square. You cannot say, okay, make this square slightly darker, slightly less bright. You cannot, right? It's either on or off. So these are a lot of the problems. So that's why the game of life is very interesting, but ultimately it's not what we're looking for when we look for an artificial life system. But despite that, it still remains somehow the face of artificial life. It's the most known system, and yeah, it's very popular. So, right, so this is for the game of life. So in the 90s, something other that was developed is the development of genetic algorithms, both in artificial life, but also in artificial intelligence as a way to solve some problems. And the very basic idea of a genetic algorithms is very simple. So you have a problem that you want to solve. And this problem can solve, usually you have an agent that's trying to do something. And what you do is that you parameterize this agent. So you give it a set of parameters that governs its actions. And what you do is you initialize 10,000 random agents with random parameters. You let them interact, and then you score their performance. And depending on the score, you either kill them or keep them for the next generation. And then you introduce some mutations or potentially some reproduction. And then you restart. And this is basically implementing natural selection for a specific goal. And something really interesting this is a video that I stumbled on when I was really young. So it's very old, from 1994. So it's these projects of evolved virtual creatures. This guy, Carl Sims, made a physics system. So here it's underwater, and you have creatures which are composed of just blocks. And then using genetic algorithms, so by doing natural selection, he selected them. Here it's selected for their ability to swim. Okay. So you have all these different creatures that learns to swim. So here I think he fixed the geometry of the creature and then taught it to swim. And we see that it's very interesting that it kind of resembles some natural dynamics, sometimes, not always, of course. But So here they're trying to learn to walk. Okay, they have some interesting techniques. Okay, this one seems a bit more natural. And so I don't know if in this iteration it was also like that, but in later iterations, the creature could also grow new limbs if it needed. Okay, so it could grow an extra arm if it needed it. Here, I think the geometry of the creatures was fixed, but yeah. And what's really interesting with genetic algorithms, which is really fun, is that the solutions you get are always very interesting. Like you would not have come up with such solution yourself. Right. So here you have more advanced stuff, and then these are ones that are taught to swim towards a specific point. So this is a very strange solution, but it seems to work, right? That's what natural selection does. It selects one solution. It does not have to be the optimal one. It's just one that works. And yeah, so this is very interesting. So this is genetic algorithms, also very related to a life. I'll let you see the video for yourself. So yeah, so genetic algorithms are very nice, also in artificial life, but they have a big problem, which is they are quite slow, at least compared to modern artificial intelligence methods, which use faster methods like gradient descent. Here you have to simulate thousands of agents, and natural selection is kind of slow, right? You have really to simulate a lot of agents and generations to get some good solutions. And of course, we touched again on this question that the open question is to design a system that displays open-ended evolution. Okay, so an evolution that keeps increasing in complexity. So if you look, for example, at this example I showed you, you start evolving new creatures. So first they start getting better, but then it flattens out very quickly. Okay, and this also happens in these kind of games where the goal is to get the cube as close as possible, or to touch the cube. Sorry. Yeah. So here you make two creatures compete. And here you would expect some kind of open-ended evolution, meaning that when one creature figures out a strategy, then you have a counter strategy, and then you keep getting better and better. But usually what you will see is that at some point somebody gets good enough and then you stabilize. You don't find more complex solution. So finding a system where you really have this increase of complexity all the time, it's really, really hard. Yeah. All right. Right. So yeah, one last thing is that, so in that case that I show you, the genetic algorithm had a goal which was designed by the human. Okay, it was either you should learn to swim, or you should learn to walk, or you should touch the green cube. But if you make a model where there is no specified goal, so you just have a system and start simulating it, the natural goal that will be implemented is natural selection, right? The creatures or things that will survive is the one that managed to survive precisely and to reproduce, right? So in some way, when you just simulate a system with no specific goal, you're actually simulating the system with the natural selection goal, right? And so an example of this was the so-called Tierra program. And this is an artificial life simulation where you have the agents that live in this world are very simple computer programs. Right? And so they are entirely determined by a piece of code. And they live inside the computer in the sense that the finite resource is the RAM space of the computer, okay? And so they implicitly compete for the RAM space, right? As you evolve, they tend to occupy the space, and then there is no more space. And so you actually see in that case, it's one of the few examples where you see some nice emergent behavior, such as self-reproduction and even parasitism, okay? So from what I've seen, it's kind of cheating, because he takes this space and he initializes it with a program that self-reproduces. And then by mutation, it evolves. But it's still initialized with a self-reproducing program. It does not really emerge, from what I remember. So there aren't any nice visualization of this system, but it kind of looks like this. So this is a representation of RAM space. And each of these color bars is a program and how much space it takes. And different colors are different species. Okay. So this is an example where you have no specific goals. You just let it evolve and you have some selection that appears. And okay, we finally arrive in the 2000s and plus. We're almost at the end of the course, yeah. So as I said, so still the game of life is king. So people are still continuing to find new stuff. And actually, there was a paper that came out. I don't know if it's a few weeks ago or a few days ago that they finally found. How do you say? They finally found an initial state which has a period of 19 and 21. And so people showed that you can set up any configuration of any period in the game of life, except 19 and 21. So this one, the one that people didn't found. And actually recently people found a way to construct these periodic. So they showed that inside the game of life, you have states that have any of the possible periods.
The periods in what, in time?
In time, yeah.
Like
So
days?
how much time steps it takes to come back to the initial state. So for example, yeah. So for example, you have a very simple state, which is a blinker, just 3 things that does like this. So this is a period of 2. And so they found a period of for 19. So people are still working on the game of life and a lot. So if you're interested in this stuff, there is this crazy book, Conway's Game of Life, Mathematics and Construction. And they really go from defining the game of life to all the steps that you need to build a computer inside the game of life. Okay. And so the kind of things that they show in this book is this. So this is a final state in the game of life. Here you have a piece of the computer, and they actually compute and display the digits of pi inside of game of life. Okay, so this is actually, it's not hard coded. The actual computer did the computation to compute what are the correct digits and then displayed them.
Isn't it strange that 21 wasn't discovered before? Because if you have a period of 3 and a period of 7, and you separate.
Okay, you're right. Maybe it was a prime period. Yes. It was not. Maybe it was not 21. That's true. That's true.
23.
Correct. Yeah. Good point. Yeah, I have to see. I'm pretty sure 19 was one of these, but there was also another one missing. Yeah. Good. Okay. So the game of life still going strong. Today, maybe a bit less because people have found pretty much everything there is. But there is a website which is dedicated to Conway's Game of Life, and there are people uploading the new configuration that they found, and there is a crazy amount of people working on this. Okay, so then from 2010, I have to speed up a bit. We have, of course, the rise of deep learning, machine learning, etc. And so we see new models appearing. And so, yeah, so artificial life and artificial intelligence, they are kind of very closely linked. They have a lot of methods which are very common. And one main thing is the shift to parallel computing. Okay, so one main thing of artificial intelligence is that pushed artificial intelligence is that you use the graphics card to simulate. And the graphics card is just a processor that can do a lot of things in parallel. And this is very reminiscent of cellular automata, okay? Because a cellular automata is natively very easy to parallelize because each state doesn't care about the rest of the system, just cares about its neighbors. So you can update every grid point independently. You can do it in parallel. So this is very important also for artificial life. So these models are very parallelizable. So the rise of graphics card, etc., for machine learning also allowed people to make models which are much, much bigger in scale. Yeah. So one thing to note is that artificial life is a research field, but it's kind of strange because at least up until now, I am hoping it will change in a few years, and it probably will. It's that a lot of research happening in artificial life is not driven by academia. So there are a lot of people which are just happen to have another job and they just do this for fun. And a lot of the new systems that we know now, they were just driven by people doing it for fun. Okay. Now it's because of the rise of deep learning, etc., and the deep roots that are between the two. It's starting to change, but a lot of the advances we'll see it was just people doing it for fun. So one of this example is Lenya, which is essentially the continuous extensions of the game of life, and also with several colors. So it looks like this. Right. So we'll explain this at some point in the course. Let me skip. Right. So this already reminds much more of like something you would observe under a microscope. Okay. So you have these kind of creatures that interact and they move. Yeah, so yeah, here you have some example of self-replication. So these creatures just duplicated. Here again. And so these colors come from the fact that now instead of each pixel being able to take either black or white, contain a continuous range in red, green, or blue. And so you have all these things which are very beautiful and that remind of some kind of biological system, but okay. And this was made by Bert Chan, which at the time just had was a IT consult. Oh, no, I think he had an informatics store and he was just doing this in his spare time. And now he actually works at Google, working on this stuff. So yeah. So then, yeah, there are a few other models that I want to talk about. So there are different extensions of this Lenya, which is continuous, which is made of particles. So there are particle-based systems, and then systems which are continuous, but where you have mass conservation, etc., etc. So all these systems are all very nice and very beautiful. So this is made by Mordvintsev, Niklasson, and Randazzo, which are also Google people. And so this is a particle version of what I showed you before. So you have this particle which interact in complex ways, and it kind of looks like cells. Right, you have oscillators, you have all this stuff. So all these models are really very nice, and they produce a lot of different behaviors. The main drawback that they have until now is that unlike the game of life, so in the game of life, you have one set of rules, and you can generate all these different creatures, the different stuff. In the case of Lenya and the particle Lenya, etc., and a little bit less flow Lenya, all these creatures that I've shown you, they exist in different physics. Okay, for each of these creatures that I showed you, you had a different set of physics for the parameters, so they don't exist in the same world. So for now, we don't really have a continuous system which exhibits the same richness of the game of life, in the sense that you have so many different creatures, so many different plants, etc. So this is one main direction of research, is actually build a continuous systems in which you have this huge variety of things, not the huge variety driven by the variety in the rules. Yes?
So when you say a continuous system, you mean that the space is continuous, but you
Right.
still have discrete particles that...
So, okay, good question. So in the case, so the question is, what do I mean by continuous? So in the case of Lenya, here we have both a continuous space-time, in fact, and continuous set of states. So meaning that, okay, to run it on the computer, you need to discretize it, of course, but it admits a limit where it's completely continuous. Okay, so for sufficiently small pixels, it will approach the continuous dynamics. And here it's also continuous in terms of states, meaning that each pixel can have a continuous set of values. And then in the particle systems, of course, the number of particles is discrete, but for example, their position and the forces they generate, these are all continuous, for example. So there are different notions of continuity indeed, but yeah. Right, and then you have also this one, which is particle life, another particle-based system, which is really beautiful. So here, this system is very simple. You have different types of particles, and according to the type of the particles, they can either attract each other or repulse each other. And the key here is also you have some interactions which do not respect the third Newton law, in the sense that you have some particles which are attracted to this one, but this one is repelled from this one. So this makes kind of a train of particles, and that's how you get these worms, right? So the purple is repulsed by the blue, but the blue is attracted to the purple, and so they start following each other. And so you get these kind of things, which looks very nice. But here again, so usually when you choose a set of parameters for the particles, you get 2 or 3 different creatures, and that's it. People haven't found a set of parameters which make you build infinitely different types of creatures. All right. And the last thing that I wanted to say, the last thing is how you can use machine learning techniques also to search through the vast space of possible rules. Okay. So one way to do this, as we said, is through evolutionary dynamics. But you can also set a specified goals and then do gradient descent. Okay. So one example of this, the most famous one, is the neural cellular automaton, which is a cellular automaton that you might think like the game of life, but with continuous set of states. So the states can be every number in between 0 and 1, not just on or off. And what people do is that they have a free set of rules, and they actually train it such that, let me go back. You start with a single black pixel, and they train the physics, okay, the evolution rules, such that this pixel evolves into a specific image. So in that case, it's a lizard. So here, every pixel can only communicate with its neighbors, okay? It's not something global. And you see it's very resistant. So I can erase its face, and it regrows. So it's quite resilient. And you can do this with any picture that you want. It's actually very easy to implement. You see? Okay, if I raise it too much, he has more trouble recovering, as you can see here, because each cell only knows about its neighbors, right? It's kind of, okay, it's making it actually. Yeah. So this is very reminiscent. Okay, you see it has the wrong number of dots. And this is typical, right? Because each pixel just sees around it. So it doesn't know how many dots there are in total, right? So that's why it fails on the number of dots. And this is kind of close to what happens in real life, right? When you have the cell that first develops, each cell doesn't know where it is exactly on the body, it just has the information from the surrounding cells. And yet it manages to grow always 2 eyes in the same place, 2 arms, etc. And it's kind of, yeah, this is a demonstration of this.
And this is trained with gradient descent.
This is trained with gradient descent. So the goal is you start with a single black pixel, and you asked it that after 60 frames of evolution, you should be a butterfly or whatever. And so we'll see this in the course also. It's very easy to implement. It's really not difficult. Okay, so let me finish with the poll. Right, so the takeaway is that we have all these different systems, okay? But despite the fact that we have ever-growing simulation power, we can do more complicated, bigger systems. As I've said, we have yet to find something that we can satisfyingly call artificial life. Okay, we don't have open-ended evolution. We very rarely have reproduction. We very rarely have very different sets of creatures. And so, yeah. So finding and solving the reason for this, so understanding why haven't we found this, something like this yet, is one of the main direction of research in the field, and it's one direction I'm actually working on and I'm interested in. So let me leave you with these ideas, which are hopefully not true. So it might be, so there is definitely a trade-off between the scale of the system and the complexity of the individual pieces, okay? So if you go at the level of particle physics, the rules are relatively simple, okay? You don't have many particle types, you have a few fundamental forces. But if you want to get something like life, you need 10 to the 23 atoms, okay, more or less. And on the other side, if you look at the scale of biology, right, the initial rules are very complex, okay? If I want to describe a biological system of cells, you have to describe an immense amount of things, right? The amount of chemicals that you have, how the cell function given each input. So here, you don't need a lot of cells to make like a multicellular being, but you have a trade-off that the individual pieces of your system are very complex, right? The cells. So there is this question that you might ask yourself is, okay, could it be that to have something like life, you require either very high base complexity, so at the level of biology, or a very high scale with simple units at the level of physics to emerge, okay? So if you think this is true, this is a problem, right? Because right now, with the GPUs that we have, we can simulate systems that have 10 to the 12 units. So this is very far from the 10 to the 23. And if you say, okay, I don't do that, I just simulate at the level of biology, we are not really able to simulate perfectly a cell, right? With all the intricacies. So it would seem from this point of view that it's impossible to have artificial life. But hopefully one of these assumptions is not true, in the sense that you can get much simpler life. And okay, so one last example that I wanted to show you, this initiative that is very old actually, it's called Open Worm. And what they are trying to do is actually simulate completely a C. elegans worm, which is a very small worm, which is very simple. It has about 200 or 300 neurons. And so what you see here is presumably, this is not perfect yet, but a simulation of the full worm. So they're actually simulating the brain by simulating each individual neuron and its connection, which has been mapped. And okay, this is not perfect, but if it gets perfect, you really have something like almost a one-to-one worm, but inside the computer, right? Which is really crazy to think about. So this is kind of the approach of doing life at the level of biology. But of course, it's not very satisfying because it's life as it is on Earth, right? It's not very generalized to other kinds of life. So let me leave you with the last poll here that will activate. All right. Let me see where I have it. To see a little bit what people think. All right. Okay. People are not too pessimistic. Seems to have two main regions. It's either very easy or very hard. Okay, so most people think it's quite hard, actually. Yeah, more than 20 years. Less than 10 years. Okay, so it's more or less uniform. So it seems that it's a very hard question. Okay, seems to show that we don't really know what will it be. But okay, very interesting. All right, so there are a few more videos. You can look them up in the website. And there is also a tentative program for the next sessions that I wanted to go through, but we'll do this next time. Just to let you know, so next time what we'll be looking at is the von Neumann cellular automaton. So we'll describe it in detail and somehow show that you have you can have a self-replicator inside it. Okay. So yeah, that's it. See you next week.